Well, good afternoon, everyone. I'm Danial Akbari, second year PhD student. The title of my thesis is Collaborative Learning for Intelligent Meteorological Aviation under supervision of Professor Javier Garcia Herras and Dr. Amin Jafari Muqaddam. So, how does it work, this one? Sorry. So I'm going to start with the motivation and the problem statement. As you may see and understood in the past presentations with my colleagues, with the contrails, this study aims to predict contrails where contrails form and actually persist, which is a problem that remains highly uncertain. Because contrails are so harmful for the climate, and as you can see in this chart that has been presented with my colleagues, in 2024 has been exceeded 1.5 Celsius with this report. And also, we are aiming to use collaborative artificial intelligence to predict contrail outbreaks and estimate their climate impact to help aircraft avoid flying these regions and avoiding forming a contrail, which is harmful. So now let's see where contrail are going to be formed. Normally, an contrail is formed in ice supersaturated regions. Ice supersaturated regions, with respect to ice, happens when relative humidity with respect to ice exceeds 100%, as you can see in the Schmidt-Appelman criteria found on 1953. And after forming a contrail, let's see what would be the climate impact of that contrail, which is the radiative forcing, which is the change in the net energy flux at the top of the atmosphere or tropopause, which is caused by particular factor. In our case, we are investigating about contrails. So it's divided into two main factors, short wave radiative forcing and long wave radiative forcing. The short wave radiative forcing is related to the cooling contrails, and the long wave radiative forcing is related to the warming contrails. And if you want to measure the total impact of that contrail, you have to sum up these two, which is the net radiative forcing that what we are looking for. So related to the previous studies in 2023 and 2024, they mainly focus on numerical weather predictions and flight trajectories and AI-based prediction frameworks in order to kind of measure and predict ice supersaturated region in global scale, and occurrence of the ice supersaturated regions in individual flight segments using atmospheric data and automated validation. But when it comes to the radiative forcing and estimation of the radiative forcing of the contrails, they mainly use observational studies of the contrail cirrus and sensitivity analysis of the contrail radiative forcing to kind of quantify warming contribution of persistent contrails under atmospheric humidity and conditions. And the other task is to demonstrate a strike dependence of the atmosphere of the contrail radiative forcing kind of on crystal size and atmospheric humidity, which is a physical term. So due to the limitations in the past study and the state of the art, we found some scientific gaps. So the first one is there is no work on predicting contrail outbreaks by inputting numerical weather predictions. So the second would be the existing models are kind of detecting contrails and identifying the radiative forcing independently, not together. And the last one that we found, contrail radiative forcing uncertainty remains very high due to the missing physical content and coupled forecasting. To summarize, our main contribution would be forecasting contrail outbreaks kind of from atmospheric predictors at different pressure levels that I'm going to show you in the results part. And jointly predicting the long wave radiative forcing and short wave radiative forcing. So the next one and the most important one is to developing a forecasting framework in order to combine many different conditions into one single workflow. And after doing all of that, the main objective would be developing a collaborative artificial intelligence framework in order to predict contrail outbreaks and estimate their radiative forcing. if we have done this, we will achieve more accurate control predictions and better climate impact estimations. So, in order to achieve that goal that I mentioned, we proposed this methodology. So we designed a deep neural network, which is called a ResNet MLP, with 2 different branches, one for classification and one for regression. So the idea is to input 8 numerical weather predictions, as you can see down below. These are the 8 weather variables, forecasted ones. And by targeting the 2 main factors, the first one is control outbreaks, which is a classification task, and the second would be long wave radiative forcing and short wave radiative forcing, which is related to the regression task. So, but here in this phenomenon, we don't have any ground truth. So we have to develop and design a target function. The target function has been designed by considering 3 different data sets. First one is the clusters of the detected contrails. Second one is the isotope-saturated regions that read from Aero 5 data set. And the last one would be flight density heat maps that is derived from ADSP data set. So by having an intersection between these 2 and applying the third one in order to eliminate the redundant regions that we don't have any flight, we will achieve control outbreaks. And if we multiply it to net radiative forcing, which is achieved from OCA product, OCA stands for Optical Cloud Analysis Dataset, we will have our main target function, which is kind of our main output. So we kind of trained the model with the whole 2023 dataset. We considered 80% of the data for the training and 20% for the validation for 3 different pressure levels, 200, 250, and 300 hectopascals. As you can see, the matrices are showing the good results. F1 shows the classification part, robustness in classification part for the control outbreaks prediction, and it's a harmonic mean of precision and recall. And recall stands for the positive values actually model can find and identifies. And when it comes to the mean absolute error and root mean squared error, which is related to the regression task, the curves are showing a reasonable decay during the validation process across 100 epochs. And the R2 is the robustness in the regression task, which is related to the radiative forcing prediction. So as for look at some experiments and some simulations, this is the whole main framework. As you can see here, the idea is to input 8 weather numerical forecasts, future numerical weather forecast, and having the control outbreaks with their net radiative forcing as outputs. So on the right-hand side, you can see simulations and an example which is related to 16th of October 2023, a day full of contrails at 250 hectopascal. And in the down below, you can see a live service that we have developed with, in collaboration with AI Methods company, which is up and running. And it can predict the same hazard up to 36 hours in 3 different pressure levels. But it's not on public yet. So as for the conclusion, this is a forecasting framework that actually couples ISSR occurrence with control clustering and also estimate the radiative forcing, which is the main goal. And as highlights, this model actually has a good skill in detection large-scale control outbreaks prediction with relativity false alarm rates. And also, it has a good potentiality in order to detect control-prone regions in clear sky conditions. So, but we have to remark the key limitations in this study as well. So, as I mentioned, this study provides a good potentiality under clear sky conditions, but doesn't consider the cloudy scenes conditions. So, which is one of the main problems. And another key limitations of this work, it does not address the microphysical evolution of the contrails and radiative forcing. So, for the future work, we are aiming to extend this framework with physical constraint and have a good variability in order to consider physical constraint for calculating control outbreaks persistent and also the radiative forcing estimation. And also we are going to extend this framework in cloud scenes with new data that we are going to get soon like MTG, like radar or balloon, or I don't know about other data sets, but we are investigated about it. And as for the achievements of the previous academic year, we presented a prototype of this model in ECAS 2025 conference. We attended to many workshops, internal, external, about the control management and machine learning on atmospheric data, how to work with that. And we submitted the conference paper on EVAC 2026 in Japan. And also, at last, and the most important one, we submitted the first journal paper and still waiting for the response from the community. And that's all from my side. Thank you for your attention.